Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about tangential and angular velocity. Let's get to it. Angular velocity or angular speed is how fast an object is rotating. How fast does it rotate? So it's a degrees or radian measurement per some amount of time. So degrees per minute, radians per hour, degrees per second, right? Stuff like that. If you think about the Earth, right, as an example, right, it spins 360 degrees in 24 hours, or if you find the unit ratio for that, then you get 15 degrees per hour, or in radians, that's pi over 12 radians per hour. Okay, that's the angular velocity of the Earth. That's how fast that it's spinning. Okay, the formula for this is omega. So that W looking thing, that's the Greek letter omega. Omega is equal to theta, which is your degree or radian measurement divided by time. Now, what we're going to find soon is that typically when we're working with angular velocity, we're going to use it to find a tangential velocity. And so theta should really be put into radians, but there are times when describing angular velocity in degrees per some time unit is a little bit more intuitive for people to understand. All right, tangential velocity or linear speed or linear velocity, that's a standard or typical distance per time unit. So like this many feet per second, right? So it's not a rotational measurement per some time unit. It's an actual distance, miles per hour, right? That's a standard speed, right? That's what tangential velocity or linear speed is. So it's how fast an object is moving around its center of rotation. So let's say that you're here. On this not really Earth-looking thing, and it spins, right? It rotates, and so you end up, right? You've traveled this distance in space, right? You haven't moved anywhere on the Earth itself, but the Earth is spinning, so you've traveled a specific amount of distance. The speed, how long it took you to get there, that speed is tangential velocity. Okay, so in what amount of time was this distance covered? Or you can think about it as how long does it take an object to move from A to B around this circle. Okay? The formula for this is V is equal to the radius of the circle times omega, omega being your angular velocity, so theta divided by time. And it does need to be in terms of radians at this point. Now, the thing that you'll notice is that velocity is directly proportional to radius, where omega is kind of like your constant of proportionality. Now, this makes sense in the context of, I don't know, you can pretend like you're spinning a piece of yarn with a bolt at the end of it or something like that. As you lengthen, right, the string, you get a more like high-pitched whirling type of sound because you're hearing, right, the speed at which the bolt is flying through the air is much greater. This maybe isn't the best example. But in any case, omega is your constant of proportionality. The whole thing is spinning, it's rotating at the same speed, but the further you are away from the center of rotation, the faster things are traveling, right? Because, even in this example, right, this distance is covered in the same amount of time as this distance. This distance is definitely larger. From A to B is a larger distance to cover than A prime to B prime, but they happen in the same amount of time. So the further you are away from the center of rotation, the faster that you're going. And I thought, maybe the string, the yarn and bolt thing isn't the best way to describe this. But I think the best intuitive way to think about this is this death machine, right? That's common on a lot of playgrounds in America. I don't know about you guys, but this thing has caused many of injury in my childhood life. But basically, the idea is, it's called a merry-go-round, by the way, but the further that you are away from the center of rotation, the more force that you feel spinning around, right, the circle, right? You kind of want to fly off. You're like hanging on for dear life as this thing is spinning around in circles. You're going to fly off. If you're at a more moderate distance away from the center of rotation, you do feel some forces, but it's not like it's going to throw you off the merry-go-round. And of course, you could also be standing directly in the center, at which case you're not really feeling any force. You're just kind of spinning in a circle. So that's why this formula, the radius really determines how fast you're going, right? It's directly proportional to the velocity, where omega, right, the angular velocity is your constant of proportionality. And then again, just as a reminder, always make sure that this is in radians over some amount of time for this formula to be accurate. Okay? So example 1, which is weird that I numbered this, right? Saying example 1 kind of implicitly implies there's more than one example, but there's not. This is the only example I wanted to go through. My parents live in Goldendale, Washington. It's a little bit east, northeast of Hood River in the gorge. So when we're doing this, it's like a 3.5-hour drive, 4 hours with stops from Albany. Along this drive, once you get into the gorge, there's all these wind turbines, right? Kind of near Central Oregon, right? In northern Central Oregon, there's all these wind turbines that generate electricity. And so when we're driving, one of the times that I was driving there, I asked myself, hey, do you ever wonder how fast these blades are spinning? And so I wanted to figure that out. So what I did is I counted the number of seconds that it took for a blade to make one full rotation, full revolution here. And it's about 4 seconds, right, for it to do that. So then omega would be 360 degrees divided by 4 seconds. Although, as I said before, we want to put this in terms of radians. So I used 2 pi, and I divided that by 4 seconds. So the angular velocity of these blades is pi over 2 radians per second. I wanted to figure out the speed in miles per hour. So I went ahead and I put this in radians per hour. And I got 1800 pi radians per hour. Okay? That's our angular velocity. Now I want to toss that into the tangential velocity formula, right? The linear speed, because I want to know actually how fast these things are moving through the air. So I Googled the average length of a wind turbine blade. It's about 140 feet. And so I just plugged these two things into my formula, right? I had 140 feet, that goes into the radius. I have 1800 pi radians per hour, that's omega. And I found out that we get 252,000 pi feet per hour. But again, I wanted this in miles per hour. There's 5,280 feet in a mile, so I divided this thing by 5,280, and I found that it was 47.73 pi miles per hour. I don't know what that is, right? If someone was like, that wind turbine is spinning at 47.73 pi miles per hour. I have no idea what that is. So I figured it out, right? Pi is approximately 3.14. So I did the multiplication, and I found that it's about 150 miles per hour. Right? That's how fast those things are spinning. All right, so that's the only example that I had with tangential velocity and angular velocity. Hopefully this was helpful. If you have any questions, don't hesitate to shoot me an email. Thanks a ton for watching, and I'll see you in the next one.